In the first class of 213, so last Tuesday, we discovered a new dimension of nature, which is electrical charge. So that was a big breakthrough. In Thursday's class last week, we explored Coulomb's law for electrical force. It told us why matter, which is made of positive and negative building blocks, is actually stable, holds together. So that was a big breakthrough. And in today's class, we got one more big breakthrough. We're going to talk about how the electrical force between electrical charges works, what's the mechanism of that, and it's a topic, the electrical field. So that's the plan for today. Specifically, I wanted to go through this list of topics here. I'm going to try and use this drawing pad. I don't know whether this is going to work, but let's see. So I'm going to introduce the electrical field. I'm going to introduce the idea of a concept of the electrical field, and I'm going to define mathematically the electrical field. So that'll be a first topic. I'm going to look at some examples of calculating electrical fields of arrangements of charge. We'll look at just a positive charge, just a negative charge, but also more complicated arrangements of charge. We're going to look at how we visualize, how we picture, how we sketch electrical fields. And specifically, we'll talk about electrical field lines. And then finally, after calculating and sketching electrical fields, I'm going to make some comments on electrical fields related to electrical conductors. Now, it's possible I won't get to this topic. It's possible we'll move this topic to the next class, but you know, I'm hopeful, I guess I would say. Okay, so that's the plan. You're going to have to be patient with me with the drawing pad. So, concept of the electrical field, definition of the electrical field. Let's talk about that. Here's the starting point. The starting point is what we call action at a distance. So the electrical force that we introduced in the last couple of classes, that's what we call action at a distance. So one charge will interact with another charge, will exert a force on another charge when those two charges are physically separated from one another. And at present, it's a mystery how that works. It's a complete mystery at how that works. In fact, another action at a distance force that you've met is gravitational force. So that's an action at a distance force. In gravitational force, one mass interacts, exerts forces on another mass at some distance with some separation, and how that works is a complete mystery, is a complete puzzle. So action at a distance was a puzzle or a problem that underlied Coulomb's law for the electrical force, and action at a distance was a problem or a puzzle that also underlied the mechanism of the gravitational force. For comparison, at the time of the development of gravitational force, development of electrical force, Coulomb force, there were other forces that were known. They're common or garden forces, everyday forces. They're like friction and they're like tension. And in those cases, forces occurred when things are touching. Forces occur when things are in contact with one another. And for those everyday forces, it was understood how they worked. They were in contact, they weren't touching, and that's how the forces were transmitting. But if two masses are at a distance or if two charges are at a distance, it was a complete mystery. It was a complete puzzle how the force was working. Okay, so the problem was solved, or the solution to the problem was introduced by a famous British scientist Michael Faraday. So he was around, more 150 years ago. He was doing experimental work 150 years ago, and he contributed enormously to electromagnetism. He's an interesting person because he grew up from sort of an impoverished English family. He had no real formal education. Rather, he apprenticed with some scientists and became a very influential scientist himself. He came up with the idea, this is the key idea, the key concept, that these forces like the electrical force and the gravitational force and also the magnetic force, when we meet that, they are carried or conveyed or mediated by what we call a field. It's the mechanism. It's how the force works. And so that's what we're going to discuss in some detail. So it's now understood that the electrical force between electrical charges is conveyed by an invisible mediator, unseen mediator that we call the electrical field. We give it a symbol. Here it is. Oh, let's got to get the pen working. We give it a symbol E for the electrical field. That's the mediator of the electrical force between electrical charges. And it's a vector quantity, like force is a vector quantity. So that's the line on the hat here on the E. It's also now understood that the gravitational force between masses is carried by a field, a gravity field. And so that's the mechanism of the gravitational force. And here's how we denote the gravitational field. It's a little G, with a hat on it, a line on top, overline, to indicate that this field is also a vector. What is sort of funny, physics funny, not real funny, is that those everyday forces, friction and tension, that were understood as simply contact forces, forces due to things touching, forces due to things being in contact with one another, they are actually action at a distance electrical forces. So friction arises, tension arises from the electrical force, the action at a distance electrical force mediated by electrical field between the atoms of the molecules of the materials in contact. So those everyday forces turned out to be action at a distance forces too, at a microscopic, at a molecular level. Okay, so now let's define mathematically the electrical field. And so that's the purpose of this this slide here, is to define the electrical field. Start by looking at this little sketch over here on the left-hand side. I've drawn two arrangements of charge. One on the left, I've called that the source charge. And then the one on the right, I've called that the test charge. So what do I mean by the source charge? What do I mean by the test charge? So the source charge is some arrangement of charge. It could really be any arrangement of charge. There's an arrangement of charge that creates an electrical field. So surrounding the source charge is a electrical field. And we're interested in measuring, exploring, or probing that electrical field. The test charge is how we explore or probe or measure that electrical field. So into the field of the source charge, I'm placing this test charge. That test charge in that electrical field will experience an electrical force. And we can define the electrical field in terms of the charge of the test charge, that's the Q naught here, and the electrical force that the test charge is experiencing. And so that argument takes us to this important equation here. It's a simple equation, but it's a very important equation. It's called the field equation, and it defines the electrical field. And the electrical field at the location of the test charge, so this location here, is defined as the force that's experienced on the test charge. So that's the F on the right-hand side of the field equation, divided by the charge of the test charge. That ratio, now these are familiar quantities. These are everyday sort of measurable quantities. The force on the test charge, we can measure that force. The charge of the test charge, we can measure that charge. And if we take the ratio of them, that tells us the field that was carrying that force from the source charge to the test charge. So it defines the electrical field for us. So this field equation is very important. It defines the electrical field, which is an abstract thing, right? You can't see it. It defines it in terms of known things that you can measure. It defines it in terms of the force on the test charge and the quantity of test charge. And so that's the field equation. Okay, so with the field equation defining the electrical field, we can combine that with Coulomb's law for the electrical field of point charges and actually write down not just the force between point charges, but now we can write down the electrical field of point charges. And so I've got two slides here. This one for a positive point charge, where we're going to write down the strength of the electrical field, and we're also picturing the electrical field that's created by that positive charge. And on the next slide, I've got a similar looking overhead for a negative point charge, where we'll write down the electrical field of the negative point charge, and we'll see the electrical field vector for the negative point charge. And I'm solving the problem of what is the electrical field of point charges by combining the equation from last class for the electrical force between charges, so Coulomb's law. I'm combining that with that new equation we met on the last slide. That's the field equation that defines the electrical field. So you can see how that works if we look at the equation on the bottom of this slide. So let's look down here. Look at that equation and ask the question, what is the field at this point? So this charge down here on the bottom left, you can think of this as an example of a source charge. It's just a single positive charge that's making a field. This charge upstairs here on the top right, think of this as the test charge. It's the charge that we use to explore, to probe, to measure the electrical field of the source charge. The electrical field at this location of the test charge, due to the source charge downstairs here, that electrical field is given by the field equation. Here it is. But in this case, we know that the electrical force between the two charges is given by Coulomb's law, because this is just a pair of point charges separated by some distance, and the electrical force is just the Coulomb constant times the product of the charges divided by the square of the distance between them. So if I plug in Coulomb's law for the interaction of these 2 point charges, and I can cancel, you can see I can cancel out the test charge. This gives me an equation for the field, the size of the field, the strength of the field, due to a single point charge. It's kq over r squared. K is the Coulomb constant. Q is the amount of charge in our source charge, and r squared is the distance of our what I will call a field point, where we're interested in the location, the strength of the field from the test charge, and that was r. And so this is an important equation. It's gotten by this combination of the field equation and Coulomb's law, but it's an equation that tells us the field of a single point charge. Now, let me comment on the direction. The direction for a positive charge is that the field is away from the positive charge. In the case of the positive charge, the electrical field on the test charge at the location of the test charge and the force on the test charge are in the same direction. we'll see that that changes when we think about a negative charge, the field due to a negative charge. So let's jump to the next slide. I'm capable. So on this slide, it's a very similar looking diagram, very similar looking equation. The only difference is really I'm going to write down what the electrical field of a negative point charge is. I'm going to do it in exactly the same way. For the field strength, I'm going to use this combination downstairs here of the field equation over here on the left. And then the field equation tells us the field at the location of our test charge, that's here, in terms of the force that's experienced by the test charge, and the field, and the size of the test charge, so the Q naught here. And so that's what the field equation is telling us down here. And then I'm just going to plug in the fact that in this case, we got two interacting point charges, the source charge on the left and the test charge on the right. And the force between two point charges is given by Coulomb's law again. So just plug in Coulomb's law. If I plug in Coulomb's law as the force between the two charges, I can cancel out the Q naughts again. And I'm left with an equation for the strength of the electrical field at the location of the test charge, at this distance r from the source charge. So again, this is this field strength of the negative source charge. Now, this equation looks the same as the positive charge. It is the same equation for the size or the strength or the magnitude of the electrical field. What's different is the difference. If you remember in the positive charge, the field was pointing away. The field vector was pointing away from the positive charge. In this case, the field is pointing towards the negative charge. So it's in the opposite direction. So just to summarize all that, by combining the field equation and Coulomb's law, we've discovered the electrical field of positive and negative charges. We've discovered that the fields surrounding a positive charge or a negative charge are in proportion to the charge, Q. They fall off with distance from the charge as inverse square, as 1 over r squared. And for the case of a positive charge, the field lines the field points away from the positive charge. And for the case of a negative charge, the field points towards the negative charge. And that result, these two slides, is really the building blocks for other work we do on computing or calculating the field of arrangements of charges. And so this is an important point. Okay, so I want to look at an example of that field equation. We've introduced the field equation. Let's look at a simple calculation involving that field equation. And so that's on the next couple of slides, are just to get us working with manipulating the field equation. So here's a problem that I've sort of set, or that I posted. And as I say, it's an example of using the field equation. So in this particular problem, we have a tiny oil drop, microscopic sized oil drop, or at least very small oil drop. We're told its mass, so its mass is 3.8 grams, and we're told that it's charged. It has a negative charge of 18 microcoulombs, 18 times 10 to the minus 6 coulombs. And we're told that it's actually just floating in space. It's floating in space because it's actually in a combination of the Earth's gravitational field and also a vertical electrical field. So if you try to imagine this charge, it's out there, it's floating in space. Here it is in the sketch. And it's immersed in these two fields, the gravitational field and the electrical field that convey gravitational electrical forces. And it must be, if it's just floating there, that there's an equilibrium of the forces. The force of gravity is being exactly balanced by the electrical force as it floats there. So the question asks us, based on that understanding, to calculate the size and the direction of the electrical field. And so we're going to go ahead and do that. And our starting point is really this understanding that's pictured in the sketch, that there's an equilibrium. There's an equilibrium between the gravitational force pulling the oil drop downwards towards the floor, obviously, and an electrical field or electrical force that's pushing the oil drop upwards. And it must be that they're in balance. And so on this slide here, I actually used that balance and calculated two things. I calculated the gravitational force that the oil drop has experienced. And then once I got the gravitational force, I was able to infer the electrical force that the oil drop was experiencing. And so let me just say a few words about that, this balance of the electrical force and gravitational force, and then we'll find the field. We'll find the electrical field. So the key point, I'm belaboring this, is that there's this equilibrium between gravity in red, that's the red vector here, and electrical force in green here. That's the green vector here. These two forces must be equal and opposite because they add up to zero. And I even pictured that, right? In this red arrow here is the downward gravitational force. This green arrow here is the upward electrical force, and they're equal and opposite. Now, the gravitational force is given by mg, the mass of the oil drop times the acceleration of gravity. And we know both those numbers. We know the oil drop was 3.8 grams. We know the acceleration of gravity is 9.8 meters per second squared. And so it was easy for me to calculate with that information what the gravitational force is. This tiny force here, about 37 millinewtons, or 0.037 newtons. So that's the gravitational force. But the beauty of this equilibrium is that must also be the strength of the electrical force. Only then can they be equal and opposite. And so the strength of the electrical force is also 37 millinewtons, or 0.037 newtons. Now, the directions are different. Electrical force must be upwards to balance the downward gravitational force, but the strengths must be equal. The sizes must be equal. Okay, so that's a big part of solving this problem. At this point, we know both the gravitational and the electrical forces. And if you think about it from the field equation perspective, from this equation perspective upstairs here, we're at a point now where we know the charge of the oil drop. It's kind of our test charge. We know the electrical force on the oil drop. It's balancing the gravitational force on the oil drop. And so we can use the field equation to actually figure out the field. And that's the next slide. That's this slide here. So I come into this slide, or we come into this slide, knowing the electrical force and knowing the charge. And based on that information, we're going to do two specific things for the electrical field. We're going to find its magnitude, and we're going to find its direction. I'm going to separate those into two distinct parts. And so let me just first talk about the magnitude of the electrical field. All we need is the field equation. The magnitude of the electrical field in the field equation is the magnitude of the force on our charge divided by the charge that's owned by the charge. So we just got to divide the known electrical force, 37 millinewtons, by the charge, 18 microcoulombs. So look, notice here, I'm not worrying about the sizes up and down for the force. I'm not worrying about the signs plus or minus for the charge. I'm just interested in the strength of the field here. So I don't need to worry about that. And so all I got to do is divide the the 37 millinewtons by the 18 microcoulombs. And if you do that calculation, I got a little over 2,000 newtons per coulomb for my electrical field. And so that's the strength of the electrical field solved. What about the direction of the electrical field? So here's my argument. This is not a calculation. This is just an argument for the direction of the electrical field. I said that, well, look, the gravitational force is downwards. That's my starting point. That means that that implies that the electrical force is upwards. Gravity is downwards. Electrical force must be upwards. The field equation tells me that, remember, it's E, which is a vector, equals F, another vector, divided by Q. It tells me if you divide by a positive charge, divide the force by a positive charge to get the field will be in the same direction as the force. It tells you if you're dividing the force by a negative charge, by a negative number, then you're going to reverse the direction of the field from the force. So the final step is that for a negative charge, the field is going to be opposite the direction of the force. If it was a positive charge, the field would be in the same direction as the force. So we knew the gravity was down. We know that the electrical force must be up. It must mean that the electrical field must be down in this particular example. And so the electrical field is down for a negative charge. Let me just give you, I love giving little bits of history on these different topics or problems. This float in an oil drop in free space under the balance of electric and gravitational fields, under the balance of electric and gravitational forces, not just an interesting problem. It actually got Robert Millikan a Nobel Prize because he balanced an oil drop under gravity, under electricity, and used it not to measure the field. He knew the field. He used it to measure the charge. And in that way, he was actually able to, he's the first person, to measure the charge on a single electron by balancing oil drops that had an excess of one single electron on it. It's a very, very famous physics experiment. Happened just over 100 years ago now. It was the first measurement of the electrical charge in an electron. It really was a remarkable experiment to balance these tiny oil drops that had one excess electron sitting on them, if you can imagine that. Okay. Enough history. Quiz question. Let me give you a quiz question on this. So let's see if I can set this up. And I'll give you 3 minutes to think about this. And so I believe I've just published the quiz question. Let me show you, at least here, the quiz question, if I can find it. Here we are. So this question says we've got two charges, and they're both positive charges. Q1 on the left, Q2 on the right. And they're sitting on the x-axis. They're sitting on the horizontal axis. And we're told that the magnitude of Q2, the one on the right, is bigger than Q1. Okay, so just think of Q2 as a big charge. You see it's a big sphere. And Q1 is a small charge. We see it's a smaller sphere. The question asks you to compare the sizes of the forces on Q1 and Q2 and compare the fields from Q1 and Q2. So are the forces the same size on Q1 and Q2? Are the fields due to Q1 and Q2? Are those fields the same size? And there's the four possible combinations of them being the same size or not being the same size for the field and for the force. Okay, it's 10:03. I'll interrupt. So the correct answer to this problem is that the forces that Q1 and Q2 experience, so they're interacting, they both experience forces, mutual forces, they're the same size, they're the same magnitude, the same strength. And one way of thinking about that is that when one object interacts with another object, no matter what the force, whether it's electric force, gravitational force, some other force, those forces always come in pairs. They're always equal and opposite. And so the force on Q1 and force on Q2 must be equal and opposite forces. They're going to have the same strength, opposite directions. What about the fields? Well, we talked about the fields of single point charges. We wrote down an equation for the field of single point charges. The equation we wrote down, which was based on Coulomb's law and the field equation, the equation that we wrote down said that the field strength of a positive or a negative charge is in proportion to the charge. So the larger charge here will create a bigger field. The smaller charge will create a lesser field. And so the field of Q2 surrounding Q2 that's due to Q2, the originates from Q2, that's bigger. That field is bigger. The field due to Q1, the smaller charge, the field surrounding Q1 that's due to Q1, that's smaller. That's a smaller field. And so the correct answer to this problem is that the forces were the same size on Q1 and Q2, but the fields that Q1 and Q2 create, those fields are different sizes. And so that's an important point. Any questions on that? I don't see any questions. Any question? If there's no questions, that either means I've been extremely clear normally, or I'm being so unclear that you actually can't possibly think of a question to ask. That it might be a little bit different on Zoom. It might be just that I don't want to ask a question. Okay, let me push on. Well, we're sort of at the midpoint now. We introduced the concept of an electrical field, a mechanism of electrical field as an unseen messenger transmitting electrical forces. We introduced the field equation, and we used the field equation for solving the field, figuring the field from the electrical force on a charge. Now I want to move on to exploring electrical fields of arrangements of charge beyond just a single positive charge or a single negative charge. We're going to put together collections of charge and explore the fields of those collections of charge. To do that, if you remember last class, we talked about the superposition of electrical forces. In this class, I'm going to mention the superposition of electrical fields, which actually underlies, is the reason why there's superposition of electrical forces. So that's the first topic. I got a slide or two, a couple of slides on this, and then we'll get into a concrete problem of superimposing electrical fields of arrangements of electrical charge. So that's basically the plan. This is my slide for the superposition of electrical fields, to introduce the superposition of electrical fields. I'm trying to get my pen running. Here we are. And you might say, well, I think I've seen this slide before, because you did see this slide before when I was talking about the superposition of electrical forces. All I've done from last class for this slide is change the word force to fields. because really the same idea of superposition applies to electrical forces and applies to electrical fields. So let me stress that the net electrical field of some arrangement of charges is the superposition, the vector sum of the individual electrical fields of those charges. So in this picture here, in this sketch here, I'm interested in the field, what we will call the field point here, sort of an abstract point, but it's somewhere where I'm interested in the field. This field here at this location arises because of the superposition of two fields. There's a test charge Q1 here. Sorry, there's a charge Q1 here, and there's another charge Q2 here. These two charges create two electrical fields, and the net, the total electrical field at the field point P is going to be the superposition of those two fields. And so I tried to picture that here. So E1, this is the electrical field due to the charge over here on the bottom left. And since it's pointing away from this this charge, we know that this orange charge, that must have been a positive charge. And at this location, the field looks like this arrow, meaning it has a strength that's represented by the length of this arrow, has a direction that's represented by the orientation of this arrow. So that's one of the component fields. The second charge is over here, is upstairs. And the field due to this charge in green, whatever this type of olive green, that's what I'm looking for, it is represented by this arrow here. So E2, the field due to Q2, is pictured by this field vector here. Remember, its length is representing the strength of the field. Its orientation is representing the direction of the field. Since it's pointing towards the olive charge, then we know that this olive charge actually must be a negative charge. Anyway, the olive vector here, that's one of the individual fields. The orange vector here, that's the other individual field. Those two fields superimpose, they sum as vectors to make the resulting electrical field. And that's this arrow here. This arrow here in teal is the sum of the olive vector and the orange vector. Add them together and you make this electrical field vector here. Now, there's two ways you could do the addition. You could draw vector E1 first. So I could draw this vector here, E1 first. That's due to the orange charge. And then at its tip, I could draw the second vector field. That's the field due to E2. So this would be E2. Then the resulting field runs from the tail of the first vector, E1, to the tip of the second vector. So that's how you can construct this electrical field, this resulting, this net, this total electrical field. But you could do it the other way around. It's perfectly fine. You could draw the second vector, E2, first. Here it is. Then I could start the first vector, its tail at the tip of the second vector, draw it, and then the resulting electrical field will run from the tail of E2 to the tip of E1. It will run along this exact same path. So the resulting electrical field is E1 plus E2, or equivalently E2 plus E1, and that's superposition. Now, in a way, this is an important slide because when we talked about superposition of forces, electrical forces, we had no explanation of why electrical forces obey superposition principle. It was just a fact, an observation, a measurement that electrical forces obey superposition principle. Now we've got a mechanism. The mechanism is that the electrical fields that are carrying the forces, that are conveying them, mediating the forces, they add together. They superimpose to make a total electrical field that creates a total electrical force. And so that's how superposition of forces is underlied, is built on the foundations of superpositions of fields. Anyway, Now we've introduced superposition principle. The point of introducing superposition principle is it allows us to go further than just thinking about individual positive and negative charges and the individual fields of positive and negative charges, to thinking about the fields that are created by assemblies that we construct out of more than one positive and negative charge. So that's what we're going to do next. So we're going to look at an example. It's sort of a classic example of the electrical field that's created by what's called an electrical dipole. Electrical dipole is just an arrangement of, it's actually just an arrangement of two charges, and one of them is positive and one of them is negative, and they have, so they have opposite signs and they have equal sizes. And so that's an electrical dipole. The electrical dipole is characterized by the amount of charge, the magnitude of the charge, the positive and negative charge. It's also characterized by the separation between the charges. So if I put them close together, my hands are close together, they're the two charges. That's a different dipole from if the two charges are further apart. Now my hands are further apart. And so this is probably, you know, the most interesting and one of the most simple arrangements of charge, equal and opposite positive and negative charges that we call an electrical dipole. I'm going to show you an electrical dipole that you know. It's the water molecule. So the water molecule, if supposing I was asked on the street, what was the most famous electrical dipole? I would definitely say the water molecule. The water molecule, as you know better than I, because you've done chemistry and I did it 50 years ago, you know that the water molecule is made of hydrogen and oxygen, H2O. Here's a picture of the water molecule. And kind of the hydrogen end of the water molecule, that's downstairs on this little picture here. That hydrogen end is positively charged. The oxygen end, here's the in red, the oxygen. That oxygen end of the water molecule, that's negatively charged. And here is the classic example of an electrical dipole. We've got a molecule with a positive end, the hydrogen end, and a negative end, the oxygen end. And that positive and negative charges, they're equal and opposite. Because overall, right, the water molecule is neutral. It's made up of equal amounts of positive and negative charge. So that these must be equal and opposite. We just redistributed the charges like we did with rubbing. A glass rod with fur or a plastic rod with silk. We didn't rub the water molecule, but it arranged itself so that it redistributed the charge to create a positive and negative end, and that positive and negative end are separated by some distance. I indicated that in magenta here. So the water molecule is very famous because its dipole moment is responsible. It's responsible for life. Water acts as a solvent. It will, for example, for sodium iodide chloride, a sodium chloride crystal, it will break up. If you put sodium chloride crystals into water, it will break it up into the sodium and chlorine ions, into the positive and negative ions. It's a solvent, and that sort of action as a solvent is crucial to life. It's crucial to how our bodies operate, our cells operate. And so without water, for many reasons, one of them is its action as a solvent, we would not be alive, and plants and animals would not be alive. And its action as a solvent is because it's an electrical dipole. And I could talk a lot about water. You know more than I. We're mostly water. There's another reason it's important. We're like 70% water. And half the rest of us is some bacteria that is not even us too. But I'm getting off topic. So I want to calculate the electrical field of an electrical dipole. That's the problem that I've set up, and that's what we're going to do now. There's two parts to this. There's part where I'm going to calculate the sketch the electrical field, and then I'm going to calculate the electrical field. So I've got two slides for that. A question from Nolan, I just noticed it. Would it be incorrect to draw the dipole from the positive to the negative charge? Yeah, so there is a convention. That's actually a very interesting question. There is a convention for which direction you draw the dipole moment, and I'm going to come back to that after we've done the calculation. So I'll mention that after the calculation. But yeah, there is a convention for whether you go from plus to minus or minus to plus. It's I'm avoiding answering it because I can never, it's a convention, like so many conventions, I can never remember what the convention is. So we're going to come to it on a slide. That's a great question. Thank you. Okay, so this slide, this slide is to get a visual understanding of what the resulting electrical field of the electrical dipole is. We're not calculating the magnitude on this slide or the direction on this slide, but we're rather picturing the magnitude and the direction on this slide. So let me go through this slide in some detail. So on this horizontal axis here, I've arranged the positive charge. I've got it over here on the left-hand side, and I've got the negative charge. I've got it over here on the right-hand side. I've placed the negative and positive charges equal distances from the origin. So here's x equals 0. This is the origin. And the positive charge is a distance a to the left, and the negative charge is a distance a to the right. So this is the arrangement of charges. And this is a dipole, right? It's made of equal and opposite charges, plus and minus, separated by some distance. The distance here is 2a. We're going to be interested in this problem, in this question, in calculating the field at some field point. And to keep the problem relatively simple, I'm going to just calculate the field at a field point on this vertical line. This vertical line is the y-axis, and it's the axis that kind of intersects and bisects this line between the two charges. So it's at right angles and midway between these two, the line between the two charges. So this, I'm drawing right angles here. I'm not just sketching or doodling. So we want the field at this point here. So to picture the field, well, all we've got to do to picture the field is picture the two individual fields and then imagine how they add up together. And we did that when we introduced the superposition principle. So this is like the superposition principle slide in a way. I've got two charges, opposite signs, and I'm going to imagine how their fields superimpose. Upstairs here, if I can draw it, this is the field due to the positive charge. The field due to the positive charge will be pointing away from the positive charge. And so I make sure to draw it pointing away, and it has some strength that's determined by the amount of charge and the distance from the charge. This line here, so this vector here, this is the field due to the negative charge. I called it E2, called the positive field E1. This is going to be, because the negative charge, remember, this is going to be pointing towards the negative charge. It's going to be pointing downwards towards this negative charge. So these are the two individual fields that we're going to superimpose. E1 from the positive charge, E2 from the negative charge. Now, notice a couple of interesting things about them. The first is that since the charges have the same size, since the field, the distances to the field point are the same distances, this is R, and this is R, then these two fields, E1 and E2, they have the same strength. So I've drawn the two vectors with the same strength, also with the same size. Also, I've drawn them such that the angle of this one above the horizontal axis, the angle of this one below the horizontal axis are equal, and they're equal to these angles here by geometry. That's a little bit of geometry. Look, this is a horizontal line. This is an angled line. The intersection of this horizontal line, or a horizontal line, and this angled line is the same upstairs here. It is downstairs here. So these two angles are also thetas. I see another question in chat. Does the direction of the field change if acting on a negative or positive charge? That's actually a good question. Let me make that clear. So Luke is asking this question. The answer to that is no. Okay, the direction of the field depends on the field, the charge that's creating the field. So if you've got a positive charge, it's going to create a field that comes out of the positive charge. Negative charge is going to create a field that goes into the negative charge. So it's determined by the direction of the field is determined by the charge that's creating the field. It is not influenced by whether there are other charges around that are going to feel that field, or maybe there's no charges around that are going to feel that field. It's just, the field is just determined by the charge that's created the field. I hope that answers that question. It's a good point. Okay, so now we got the individual fields. I've drawn a vector which is my sketch of the superposition of the two. And look, here's a really interesting thing. E1 was going to the right and up. E2 was going to the right and down. Their horizontal, their to the right components add up. I drew that. So the resulting field is to the right. Their vertical components, one's going up, one's going down. They're equal size. Their directions above and below the horizontal axis are equal. They're equal to theta. Their vertical components cancel out. And so the sum of the two vectors, which I might picture like this, if I added E2 and then E1, or I might picture like this, if I added E2 to E1, the resulting electrical field is horizontal. And it's in a direction, the same direction as the direction from the positive to the negative charge. And so that's what I've drawn here. So on the next slide, I'm going to try and calculate the size of this electrical field. So let's see how we do that. Okay. So this slide is all about the size of the electrical field, the size of the resulting electrical field. How will we calculate the size of the resulting electrical field? Well, the first step is actually to calculate the size and the X and Y components of the individual electrical fields. And so that's covered on this slide here. This slide is going to tell us what the size of E1 is, what the size of E2 is, what the size of E1X, E1Y, its X and Y components are, what the size of E2X, E2Y, its X and Y components are. So let's take a look at that. I'll go through E1 in more detail, and then I'll go through E2 downstairs here more quickly, because it's the same approach for E1 and E2. There's just a small difference for E1 and E2. So let's take E1. What's the strength? What's the size? What's the magnitude of the field due to charge Q1 that we're calling E1? Well, that's given by basically Coulomb's law. This little expression here is just K times the charge, which is Q1, times the divided by the square of the distance we are from the charge. That's the square of this R square, the square of R. So that's the electrical field strength. If we want the components, well, if I want to picture the components, I pictured them here. Look, that's the horizontal component of E1x. This is the vertical component, E1y. They represent the adjacent and opposite of a right-angled triangle whose hypotenuse is E1 itself, whose hypotenuse is this length. And so if I want E1x, I just need to take the multiply the hypotenuse by cosine theta. If I want E1y, I just need to multiply the hypotenuse by sine theta, and that will give me E1x and E1y. Now, I do have to be careful about the signs. I'm going to use the sketch to guide me on the signs. Look, this vector here has a positive x component. It points towards the right. This vector E1 also has a positive y component because it's pointing up. So I put in a plus sign here, put in a plus sign here by hand, because from the sketch, I knew that E1 has positive x component, positive y component. The same calculation works for the field E2, that's this guy downstairs here, due to Q2, the negative charge. The strength of that field is just given by Coulomb's law again. It's KQ, the magnitude of this charge, divided by the square of the distance we are from that charge. That again is R. R is this distance here. Again, if we want the x and y components, well, let's consult the sketch. This vector E2 here has a horizontal component. We call it E2x. It's this component here. Has a vertical component. It's this component here. Those two components make up the adjacent and opposite of a right-angled triangle whose hypotenuse is E2. Same sort of right-angled triangle business. If we want the x component, E2x, we just got to multiply by cosine theta, the hypotenuse. If we want the y component, we just got to multiply the hypotenuse, the magnitude of the field, by the sine of the angle in this triangle to get the opposite side of the triangle. That's what I did here. Multiplying by cosine theta gives me the adjacent, that's the x component. Multiplying by sine theta gives me the opposite, that's the y component. There's one important point here. Again, I used the sketch. I consulted with the sketch when I wanted the signs of these two components. E2x is in the positive x direction. So that's towards the right. E2y is in the negative y direction. It's downwards. And so that's the minus sign here. That's the plus sign here. Okay, so now we got our x and y components. We're almost there. We're almost there to finding what E itself is. So let's go on to the next slide and take a look at that. So this is our final slide. There's a question in chat. Safia, if I'm saying your name right. Maybe I'm not, in which case I apologize. So will downward components always be negative? Well, that's an important question. If you choose the upwards direction to be positive, then downward components will always be negative. I could have done this problem solving with upwards being negative, and then I would have to have chosen downwards to be positive. So there's a choice that goes in here. What direction you're going to call plus, either up or down, but once you call one up plus, downwards is negative. Or if you call downwards plus, then upwards would be negative. So that's the answer to that question. Okay, jump into this slide now. This is where we're going to calculate the x and y components of the resulting, the total, the net electrical field. So that's the EY and the EX here. To find EY, we just got to add the two y components, E1y and E2y. And if you look back on the previous slide, and even if you consult the picture here, remember that they're equal and opposite. One is up and one is down. Their sizes are the same, and so they cancel out. There's no y component to the resulting vector here. What about the x components? Well, the x components will be the sum of E1x and E2x. They were both the same size. They were both kq over r squared, the strength of the individual electrical fields, multiplied by cosine theta. And so the resulting electrical field in the direction to the right, in the horizontal direction, is just 2kq over r squared times cosine.
Sorry, I'm trying to listen.
Times cosine theta.
Okay.
So here I've rewritten that expression in an alternative way. Cosine theta in here. This is the cosine theta, if you remember, is the ratio of the adjacent side of a triangle to the hypotenuse of the triangle. Well, this triangle down here, oh God, that was really bad, is a equivalent triangle to this triangle over here, which is also really bad. The ratio of the hypotenuse to the adjacent of this triangle is the same as the ratio of the hypotenuse to the adjacent of this triangle. And so I've just replaced cosine theta with a over r. So the reason I did that is that this here tells me a very interesting thing about the resulting electrical field of the dipole. Actually tells me two very important things that I tried to stress here. One important thing is that the electrical field of the electrical dipole, it doesn't fall off as the square of the distance. It falls off as the cube of the distance that you are from the dipole. So as we increase r and get further and further away from the dipole, the field is not falling off as the square, it's falling off of the cube of the distance. And that's because we're superimposing this positive and negative charges. And what's left over falls off as the cube of the distance, not the square of the distance. It also, if we look here, this equation tells us that the strength of the field of the electrical dipole not only depends on the amount of charge. So if you have more charge, you're going to get a stronger electrical dipole. But it depends on the separation between the two charges. So the greater the separation between the two charges, the stronger the field. This quantity here, Q times 2A, even the size of the charge times the separation of the charge, is called the dipole moment. And the field depends on the dipole moment, not individually so much the charge and the separation, but the product of the charge and the separation. So those are the two key takeaways for the electrical dipole. The water molecule is so important, is such a good solvent because it has, for a molecule, it has a large amount of charge Q that's separated by a large distance 2A. That makes it a strong electrical dipole. That makes it a very strong solvent, and that's an important property for life on Earth. Okay, that's the electrical dipole. I want to turn finally to sketching electrical fields. So this is the final topic, and we're just going to walk through how we sketch electrical fields. We sketch electrical fields by sketching field lines. And here's a sketch of the electrical field lines of a single positive charge. So in the center is the positive charge. Here's the positive charge. Now I've obscured it, but here's the positive charge. And when we sketch field lines for a positive charge, we sketch them as emerging radially outwards. And so you see these spokes, like spokes of a wheel, they're emerging, these are the field lines, and they're emerging radially outwards of this positive charge here. Now, the key things about field line sketches is that the magnitude or the strength or the size of the field is given by how closely packed the field lines are. So look, close to the charge, the field lines are closely packed. And so that's a region of strong electrical field in here. Far from the charge, here's further from the charge. The field lines are weakly packed. So this is a region of much weaker electrical field where the field lines are loosely packed. So that's the magnitude of the electrical field from the field lines. What about the direction? The direction of the field lines point in the direction of the electrical field. So, for example, upstairs here, the field above the positive charge is upwards. Downstairs here, the field below the positive charge is downwards. If I was on the left, the field would be towards the left. If I was on the right, the field would be towards the right. So we know the field is away from the positive charge, and the field lines point in that direction away from the positive charge to tell you the direction of the field. Just a couple of remarks here. Field lines always start on positive charges. You can never start a field line just in free space. It has to start on a positive charge. And the second point, field lines never cross one another. They will never cross one another because it would be ambiguous as to which direction the field would be. So those are two rules. One other point is, note that this I'm drawing, of course, I'm drawing a two-dimensional sketch of a three-dimensional field. So we have to remember that when I'm trying to sketch something that exists in 3 dimensions in this two-dimensional picture. But still, nonetheless, field line sketches are very helpful in understanding electrical fields. That was a positive field of a single positive charge. I want to show you the electrical field of a negative charge. And here it is on this slide. Let me clean this slide up if I can. So in this slide, I've now got a negative charge. Here it is. And I've drawn surrounding it, in the space around it, the field that it creates by drawing the field lines for the negative charge. And so these spokes that run inwards for the negative charge, these are the field lines of the negative charge. The magnitude of the field is again representing, so the field magnitude is represented by how densely packed or loosely packed the field lines are. So in this region close to the charge, they're tightly packed, they're densely packed, so this is strong electrical field. In this region far from the electrical charge, they're loosely packed, and so this is a much weaker region of electrical field. The direction of the electrical field is given by the direction of the field line. So if you're upstairs here, the field lines are pointing down. The field is pointing towards the negative charge, as we've discussed before. If you're downstairs here, the field lines are pointing up, pointing towards the negative charge. If we're over here on the left-hand side, the field points towards the right, the negative charge. We're over here on the right-hand side, the field points towards the left, towards the negative charge. So the direction is encoded in the direction of the field lines. Again, just these few points. The field lines started on positive charges. That's the only place they can start. And they end on negative charges. They only end on negative charges. And the field lines never cross. They can never cross one another, because if they did cross one another, it would be ambiguous what the direction of the field is. And again, remember, we've got to be a little careful. I'm drawing a two-dimensional sketch of a three-dimensional field. Let me show you a couple of other in the last 4 minutes. Let me show you another couple of field line plots. If I can manage to get off this slide, which means controlling the pen. Here's the electrical field of the dipole. This is the problem that we solved in the last part of the lecture. We had a a positive charge on the left, we had a negative charge on the right, and we figured out the field along the midpoint. And if you remember, we found that the field along the midpoint pointed from left to right. So here would be a field vector, and it got weaker as 1 over r cubed, meaning it gets weaker quickly as you walk away from the center point here between the two charges, upstairs or downstairs. The field gets weaker very quickly by 1 over r cubed. This is what the entire field pattern looks like. If you were close to the positive charge, look, the field lines are densely packed, so the field is strong here. And actually, the field is almost radially outwards of the positive charge. If you're close to the negative charge, the field, again, is strong and is pointing in towards the negative charge, radially inwards towards the negative charge. Along the midpoint, as we said, the field points simply left to right. The field lines are coming out of the positive charge and being collected by the negative charge. If you were very far from the dipole, so way down here or way, can't find the pen anymore, I don't know where it went, way upstairs here, then the field would be really weak. One more, I think. I want to show you one more. I want to show you, and I want to show you this because we're going to come back to this in later classes. This is the electrical field of a positive plate over here on the left-hand side and a negative plate over there on the right-hand side. So here's a positive plate on the left-hand side. Here's a negative plate on the right-hand side. The positive plate is a source of field lines. The negative plate is a kind of what we would call a sink of field lines. This is where the field lines end. So they end on the negative charge. They begin on the positive charge. And this is a very interesting field. If you have imagine two plates, two flat plates. This one's positive. This one's negative, standing by one another, parallel to one another. You create this beautifully simple electrical field that simply sweeps from the positive plate to the right-hand, to the left-hand negative, right-hand negative plate. It's a uniform field, same strength everywhere in that region between the two plates. It's uniform direction. It's always from the left to right between the positive and negative plate. And so this is another, as well as the dipole, this is another very, very, very famous electrical field. Okay. I'm going to end there. Let me just recap. Let me steal a minute from you. We introduced the concept of the electrical field as a mediator of the electrical force, and we defined it with the field equation, E equals F over Q. We looked at the fields of a positive and negative charge. The fields fall off radially as R squared. They depend in strength on the amount of charge, and the field lines go into a negative charge, emerge from a positive charge. We talked about superposition of electrical fields. We superimposed the fields of a positive and negative charge, and we said that was an electrical dipole, a very important charge distribution. Water was an example of that, and we found that field, this was really interesting, that field fell off as 1 over r cubed. Not 1 over r squared, 1 over r cubed for an electrical dipole. And it depended on not just the amount of charge, but the separation of the charges. And then finally, in this last little bit of the lecture, we looked at how to sketch electrical fields. We looked at the sketch of the positive and negative charges electrical field with field lines. We looked at arrangements of charges. We looked at the famous arrangement of a dipole, and we looked at this famous arrangement of a positive and negative plate, which is a bit like a dipole. Anyway, that's the end of the class. Thank you for putting up with this class being on Zoom, this class being online. I had to remember how to dig out my pen and learn how to do that again. I think I only partially did that. I'll hang on here if you've got questions, and I'll try and answer any questions in chat. So thanks, everybody.